Hello and welcome to the lecture Convolutional Neural Network Part 3. In this lecture, we are going to discuss different optimization issues like vanishing gradient problem. In this particular lecture, we are first try to understand that deeper network is not always good. What are the major problem of deeper network? Then we introduce the vanishing gradient problem in activation functions and the vanishing gradient problems, and how the vanishing gradient problems being solved with activation function, and what are the problems with activation function to solve the vanishing gradient problem. In the previous lecture, we have studied various deep neural network, mostly convolutional neural network. Now we start today's lecture with the evaluation or comparison between deeper nets versus shallow nets. It is very obvious that deep neural networks contain more number of hidden layers between input and output layers, which allows them to learn complex patterns in hierarchical fashion, or you can say that it can model more and more complex models of data or complex distributions of data in a different level of abstraction, starting from initial level to the deeper level, where initial levels are mainly model the primitive patterns, and the deeper level is more complex and more complex patterns. And this hierarchical feature learning gives a kind of advantage or make it more successful in computer vision tasks like image recognition, like some NLP task and speech processing recognition tasks. Definitely, another major reason of its success that it trained on a huge data set, the large data set. So these are the definite advantage of deeper nets. But at the same time, deeper nets, since it is a bigger network, it requires more computational resource like GPUs, longer training times, and some careful designing techniques to get rid of overfitting or vanishing gradient issues. So in this lecture, we are mainly focused how to overcome these design issues or how to get rid of vanishing gradient like problems for deeper networks. But before that, we should understand what are the advantages and disadvantages of the shallow or conventional neural network. In shallow nets, it has only one or few hidden layers. Definitely the simpler, faster to train and require less computational power. This design wise, these are simple, easy to implement, require less computational power, but it's not that much accurate or that much powerful for complex tasks like image recognition, semantic segmentation, and different context recognition or context modeling task. So the major disadvantage of shallow network is that it struggles to capture intricate relationship in data. The deeper network can easily do. So definitely The choice between deeper and shallower network depends on complexity of the problem, depends on the application, the problem at hand, and the amount of available data. In supervised paradigm, we say available and annotated data, and definitely the computational resource. That are the most important parameters by which we can choose a deeper net or a shallower net. This was the now the major question arises: is the deeper net is always better? If we have a provision, can we go for always the deeper net? We just look at this diagram. This is on cipher 10 data. Now here you can see that this is a test error, that 20 layer, that means the shallower net is, the error is lower, that means its performance is better than the deeper layer and 56 layers. This may be a reason of overfitting, because we know that in general the complex model often face this overfitting problem. This is a good at training error, but not that much good at testing or generalization. So they are more generalization. But very interestingly, this is in training case also. This 20 layer model is performing better than the higher layer models. So that means it is not the overfitting, also not the reason. It's something else, or something more is there. So we can say in principle, adding more layers increasing the network capacity as deeper layer do, enabling it to learn more complex and hierarchical feature representation. However, this greater capacity sometimes raise the not only risk of overfitting, but some optimization challenge. So very deep network often experience optimization challenge, or that prevent them from fully utilizing their theoretical capacity. So these are the some observation that we can say the deeper may not always the better if we not take the some sort of measure or care to implement the deeper network. So one problem apart from this overfitting problem is credit assignment problem. As depth increase, this credit assignment problem becomes more severe, making it difficult to gradients to propagate effectively through many layers during the propagation. Very briefly saying, the credit assignment problem is basically due to that some upper layer neuron or deeper layer neuron always assume that their lower layer neurons perform very correctly. On the other hand, some lower layer neurons always assume that upper layer neurons are correct. But in practice, this may not be. Due to this issue, there the problem happened, and that is called credit assignment problem. Due to the time limitation, I'm not elaborating here, but there is a important problem, and you can go and discuss any of the textbooks and materials available on the students. So what we can understand here, these kind of problems, that this kind of optimization problems, like credit assignment problem, vanishing gradient problem, these deeper models achieve higher training error than their initial counterpart despite having repeated skills problem. So that is very important to understand. So what we conclude, that simply increasing network depth doesn't guarantee improved performance. We need effective architectural design such as residual connection, normalization techniques, appropriate optimization strategies often required to train deeply. So some optimization technique, maybe from architectural viewpoint, maybe for activation function viewpoint, many other different strategies can be possible to solve this kind of optimization degradation of the department. What we have understand and observed in our previous discussion, for a deeper neural network, vanishing gradient problem is a major issue. So in this lecture, we try to understand what exactly vanishing gradient problem is and how to handle it. So vanishing gradient problem is a fundamental optimization challenge encountered when training deep neural network using gradient-based learning algorithms such as backpropagation. So what does this mean of this statement? Now we say that it is an optimization challenge. So it's the issue of the optimization algorithms. What kind of optimization algorithm? That it's like gradient descent algorithm, which has been used as a backpropagation for training of the deep neural network. So why this kind of problem, or what is actually the problem is? To understand this, we have to go back our backpropagation concept. During backpropagation, gradients are computed repeatedly applying the chain rule to the multiple weights that we have seen in our neural net lectures. That in general, the successive layers, definitely from the output layer to input layer. So in a backward direction, the successive hidden layers are basically provided the gradient of error using the chain rule. What chain rule is basically doing? It is multiplying with these error gradients. Just for example, if we use sigmoidal nonlinearity, the derivative of gradient means derivative. So gradient derivative of this is yg into 1 minus yj. If yj is L. Now, if this is the thing, and this thing is less than 1, even it is for tan h function, it is also specifically this function is less than 1. So when activation functions such as sigmoid or tan h have derivative less than 1, the repeated multiplication of this small derivative cause the gradient to decrease exponentially as they propagate towards the earlier limits. So what we can understand from it, that since the derivative of these activation functions are in general less than 1, and using chain rule we are keep on multiplying the numbers which are less than 1, what happens? It is decaying, it is exponentially decaying. And when from the backward, the deeper layer to earlier layers, when you go, and if this number of layers is too high, so too deep network, so it generally the error of gradient or gradient of error, whatever, this is decaying exponential, and this cause that if the gradients become very close to zero, then the weight updation, mainly in the initial layers, is becoming a very small, almost negligibly small. So there, the process of convergence become infinitely slow, or it is almost stopped. This is the situation where we can say that this gradient is vanished, and that's the name, the vanishing gradient, vanishing gradient. Let's try to understand in more detail. So in this process, as a result means of this decaying, the weights in the initial layers is extremely small updates, significantly slowing or even preventing learning. Learning means convergence. So if this problem happens, it restricts the capture the long range dependencies, mainly in the sequential and the learn effective low level feature representations for the spatial learning, leading to a poor convergence and suboptimal training performance. And that is why gradient is exponential decaying when you go to the upper layers, or if it is a only square. So although the deeper networks theoretically possess greater representational capacity or expressive ability, the vanishing gradient problem makes them difficult to optimize in practice. It is not converging at all. How can it happen? So modern deep learning architecture mitigate this issue using some technique. We may use ReLU activations, rather sigmoid or tanh activation. Most important is residual connection, skip connection, batch normalization, careful weight initialization, etc. and adaptive optimization algorithms, all of which facilitate more effective gradient propagation. So there is a lot of different way to handle, but in this lecture we basically try to understand how the activation function can be chosen to mitigate this problem. And in the next lecture we'll see the residual resolution of this problem. Now, first you have to understand properly what the vanishing gradient problem is. We have to look back at backpropagation. This slide, I think you can recall in the last lecture, that this is the final layer where we actually find the error. The D is the your predicted output, small d is the target output. You take the minus difference, at the square and normalize it. You get the error. And this error is taken the gradient of it by this technique. And different hidden layer from output layer to input layer, so in backward direction, this the gradient of error are propagated in this way by the use of chain rules. Okay. So this fine. And then every layer, this weight updation algorithm is basically used. That everywhere is WEYWHK minus 1 is basically done in this way. So this is as a whole a summary of backpropagation. So in the vanishing gradient issue, when we do the backpropagation to learn a particular neural network, or a deeper network. So here what we have taken, that is a kind of 4-layer neural net, just for our understanding what is actually happening in case of backpropagation. So as we have seen in the last slide, that there is a forward pass and there is a backpropagation, that means weight updation in the backward direction, that means from output layer to input layer. So now this is the, say, this the first hidden layer, second, third, and the output layer, and in before there is the inputs come. So this is the basic setup. So in case of backpropagation, what we have seen, that these gradients are basically calculated here first, and this is the final error, and this error gradient through chain rule is going to the successive uh, hidden layers, and these hidden layers basically use this gradient for this weight application, from this to this, then this to this, and by these chain rules equations and so on, that we have seen our backpropagation. Now what actually happening that in backpropagation algorithm, here we start step by step and see what is going to happen. Now here we can understand, although this is the EY, that this is the error, this D of EY by D of WY, that is basically error gradient at this layer, and accordingly we can update these errors, and this is the, so we start from here actually, and we want to find this because ultimately we coming here because this is the first hidden layer. So from we start here, we propagating output layer to hidden layer 3, then layer 2, then layer 1, and so on in this way. So we start from here, we start this procedure here, and we are going to go here. So that is the ultimate backpropagation thing. Now what we start from one step by step, that what is basically happening. First step, it is done by this, that we use a chain rule, that this level, how we find del of ui of del of h3. So this level, this talks. So to calculate this weight, we need this error propagation at here. What is the error gradient, and this error gradient we can find this from this chain rule. Okay, and the similar thing, if you go for h2, then you can find that this e of y of wh2 is this is the chain rule. This is the hypothetical 4 layers, so that's why it is looks very easy. And finally, when you go there, these chain rules we have used, so we can find d of ey of d of h1, that is the error gradient of here of this, and this is the chain rule equations, so that we can get the gradient here, so that we can find the what are the wh1, how the wh1 will be calculated. So this is the basic understanding of the backpropagation algorithm. Now what happened? So the vanishing gradient problem appear, that what happens if the derivatives are small. So now what we understand here, if it is a big issue, now here it is a only 4 layer, that's why it looks only 4 multiplication. Now if it is a 40 layer, so there is a 40 multiplications. And what is actually happening here, if these things, these values, that particular these values are basically, these derivatives are very small, Small means less than 1. So when these derivatives are small, the gradient signal progressively diminishing is progressively reducing or decaying as it backpropagated through the network. That exactly happened through this. As we have seen that in every when we backpropagate from layer by layer, from the output layer to input layer, so these basically these derivatives are becoming smaller and smaller, and exactly it is happened due to since these are the less than 1, and we are multiplying, so it will. So ultimately when we do the same, the here h1 or close to h1 h2 something for a bigger network, then these values become very close to 0 because we are keep on multiplying with uh, small numbers. Okay, so then what happened that during backpropagation, gradients are strong near the output layer that we find, but become progressively smaller toward the input layer with the repeated multiplication of values less than 1 that we have seen. And due to this, that you again come here, that where we find that our weight updation algorithm. Now, if these values, this thing, this is the error gradient, and this is this h. If this hk minus 1 where this is k is equal to 0, or that means h1, h0 now means we can say k is equal to 2, that means h1, or it's a 3 and h2 and so on. But this is the very close to the initial, close to our inputs. These layers, these derivatives, the d of uy by d of hk minus 1, these derivatives come very small or very close to 0. If it is very close to 0, then whatever learning rate is that, if we multiply, then it's also very close to 0. Now we are subtracting a value that is very close to 0. That means what? These are more or less same. So there is no such weight updation is occurring. There is no such weight updation is occurring when this network is higher, deeper. So that means if no such weight updation is occurring, then the convergence become infinitely small or slower, or almost there is converging process is being stopped. It's almost, and that is the problem of vanishing. So that why as the gradient decays during backpropagation, weight updates in the early layers become negligible. As a result, learning slows down or may stop altogether. This is the known as the vanishing gradient. Now we try to understand that we understand that what actually happening the vanishing gradient, or why it is so you can say important for specifically when the network are deeper. Okay, so this is one of the major issue, and we have to see how to handle this. Okay. Now next, what we will going to understand that how to solve this. But if we have to solve this, then we have to understand few things. First, it may be, I should not say the completely, I say partially at least been rectified or somewhat repaired, choosing the activation function judicially. Now, how or why or what activation function we should choose to make this vanishing gradient problem a bit lower. For that reason, we have to go through these activation functions very in detail. So as of now, we mainly discuss these four activation functions. That first of all, sigmoid and nonlinearity. That s of z is equal to 1 by 1 plus e to the power minus z. That we know, we almost many times we have gone through this, and this is this curve, and it very close variant is tan h function. It is hyperbolic tan. That is just you can say that is a kind of a shifted sigmoidal function. Only it is going to this 0, and this is the tan h function. Another is ReLU function, that when it is greater than z is greater than 0, then there is a some values there, positive values, and on less than 0 it's and leaky ReLU, that this is when it is greater than 0 it is more or less same of the ReLU, but when less than 0 there is some very small values, but still this is called leaky ReLU. So these are the four variants. Now we have to understand how we have to choose, how we judicially choose this among these functions, so that this kind of vanishing gradient problem to some extent we can repair. Now first, to understand first that what is the problem with sigmoid and nonlinearity in case of vanishing gradient problem. Now sigmoid squashes the inputs to range 0 to 1, that we know, understand very well, that it is basically for a and that's why it's called the this logistic function, so that it basically used for classification task. So sigmoid squashes into input range 0 to 1. So when the neurons become saturated, their output close to 0 1, the derivatives approaches 0, effectively killing the gradient during backpropagation. So that is a very interesting thing you can see, that when these values is basically there, so you can say that it's a very nearby position. So these are the derivative of sigmoid, and it is basically closing to 0, or here also here. So maximum derivatives is 0.25. It's a way less than 1. It is on 0, and when these are the close by values, it is 0. Derivatives are very close to 0. Now, what is this? Now, this dl of ds is basically multiplied to this ds of dz. Okay. Now, this value in backpropagation, dl of ds is multiplied with a small ds of dz, decaying the signal to the next layer. Absolutely, this is going to happen because this ds of dz is very less than, way less than 1. The gradients gradually vanish during it. Once they become nearly 0, gradient flow stops, preventing the neural network from running. So this is the problem with sigmoidal nonlinearity, and that's why sigmoid function is not very good for a deeper network. So it effectively kills the gradient in the long backpropagating series. Okay. So that we summarize, saturated neurons with output very close to 0 have near 0 derivatives, effectively killing the gradient during backpropagation. Near vanishing gradient problem is not 0 centered, and ex is the e to the power x is exponentially expensive. So these are the major disadvantage with sigmoid and nonlinearity. Next come with hyperbolic tan. This is squash the number to -1 to 1. It is also 0 centered. Say that is also zero symptom. It also kills gradients, causes the vanishing gradient. And tan H is just a scale version of sigma, so it's more or less similar equation. So it is also not very useful for the deeper structures or deeper network. Now, the major improvement done by rectified linear limit is popularly known as ReLU activation function. One positive thing here that it does not saturate in the positive region. Okay, and it is computationally efficient because it's a kind of linear, and it converts Pascal sigma tan H. Because of this, if the value of z is greater than 0, then the vanishing gradient problem is not a big issue here. But there is one issue with this. It's called dying ReLU problem. What does this mean? If a neuron's weights are updated such that its neuron is always negative, the ReLU outputs remains 0. Since the gradient is also 0, the neuron stops updating itself, effectively dies and no longer contributes to the life. Definitely it is better than sigma and tan, particularly when the value is 0. But it has this dying ReLU problem. Okay, so this is the one of the activation function that people use in the kind of deeper structure. Somewhat some improvement done on the case of algebra. Next, another variant of ReLU, it's called leaky ReLU or leaky rectified linear unit. This activation function value 0 1 is arbitrary alpha in a max of a of this alpha z and z and any small positive constant. Right, z basically is alpha. Solves this basically this is proposed to solve the ReLU's dying neuron problem. Avoid zero gradient by introducing a small slope. That means this small slope. So it does not suffer from the saturation at this point. Computation efficient, typically converts faster than sigma and tan H characters. So this is a kind of a bit more improvement over ReLU in even in case of sigma in the vanishing gradient issue. Now we can choose this kind of activation function for somehow manage this, but is that enough? That is a very important question. Now, activation functions are not enough to handle the vanishing completely, and that is a very important observation for the deeper layer or deeper network, mainly in Google Net, and it's a very deeper network. So first we start with leaky ReLU. What is the most improved version of this kind? This leaky ReLU reduces this problem but does not eliminate the vanishing gradient. For negative inputs, its gradient is small but non-zero, typically alpha less than 1. During backpropagation through many layers, these gradients are repeatedly multiplied, causing them to decay exponentially. So still there is a problem. As a result, very deep networks can still experience vanishing gradients, although the effect is less severe with standard ReLU sigma or tan H. So leaky ReLU is good but not enough. Now, why leaky ReLU is not complete solve the vanishing gradient? So because this small negative gradient is there. For negative inputs, leaky ReLU is a small slope. It's alpha, 0.01 maybe or something. Although the gradient is non-zero, it is still less than 1. So repeated multiplication across many layers cause the gradient to slope. So that is the issue. Actually, this small negative gradient, this alpha, is basically to solve the problem of dying radio, not vanishing radio. So it's primarily addressed the dying radio. Leaky radio is designed to prevent new neurons from becoming permanently inactive or dying radio, not completely eliminate the vanishing radio. And there is another issue, that cumulative gradient decay. Even without zero gradients, repeatedly multiplying gradients smaller than 1 in backpropagation cause them to decay exponentially, making training a very deep network difficult. To effectively address the vanishing gradient problem in very deep network, architectures such as residual network resonate or use the residual skip connections allow gradients to bypass one or more layers, a gradient flow, and enabling success training much deeper models. That we will understand. So in this lecture, we basically cover these important issues, that the deeper network is not always good. What are the actually problems of the deeper network? Then we try to understand vanishing gradient problem, mainly is for the deeper network, activation function and the vanishing gradient problem, and what are the problems with activation function to solve the vanishing gradient problem completely. In the next lecture, we'll start the residual network. Thank you very much.